Hi everyone, this is Mrs. J, and today we're going to be graphing cube root functions. Alright, I have a quick warm-up for you guys before we get started, so if you could pause the video and give it a try, that would be great. Alright, go ahead and check your work here. Just remember, when you're taking the cube root of a negative number, the result is a negative number. So you end up with a graph that looks something like this, and the domain and range are both all real numbers. So today we're going to be graphing our cube root functions using transformations. So this is going to be very similar to the last lesson when we were graphing square root functions. So just a quick review of the different transformations. If you see a negative out front, that's going to be a vertical reflection. If you see something multiplied to the front, that's going to be a vertical stretch or shrink by a factor of a. If you see something multiplied on the inside of your cube root, that's going to be a horizontal stretch or shrink. But here, just be careful, the stretch or shrink factor is going to be the reciprocal of b. And then here, this will shift our graph left or right. And remember that we'll always move in the opposite direction due to that negative sign that's built in. And then this will shift our graph up or down. Now you might notice for this that I didn't include a plus or minus inside. That's because for cube root functions, a vertical reflection actually generates the same exact graph as a horizontal reflection. So anytime you have a negative on the inside, we can actually simplify it. The cube root of -1 is just -1. So I'll move it out front and we will treat it as a vertical reflection. Additionally, if the stretch or shrink, this b value that you see here, if it's a perfect cube, I would recommend actually taking the cube root of that number and moving it out front, turning it into a vertical stretch or shrink. So I think that would make the problem easier. It's not required, but it's something to look for. So we're going to take 3 of our coordinates from our parent function, these 3, and we're going to transform them using our basic rules of transformations. But before we do that, I want to think about one question. So why is the domain of our cube root functions different from square root functions? So remember, for square root, we always had a restricted domain. For a parent function, it was from 0 to infinity. And the reason for that is that you can take the cube root of any number. You can take the cube root of a negative number, you can take the cube root of 0, you can take the cube root of a positive number. So since you can take the cube root of any real number, there are going to be no domain restrictions. Where for square roots, we can only take the square root of a number that is greater than or equal to 0. So a slight change there and just something to be aware of. All right, let's give this first one a try together. So first I'm going to look at our equation and decide what transformations we see. So I see a vertical stretch by 2, by a factor of 2. And remember, anytime we have a horizontal reflection, we can actually simplify this. The cube root of -1 is just -1. So we can treat this like this. We could also leave it as a horizontal reflection. You'll get the same exact graph. I just typically prefer to make things vertical or to simplify them if we can. So we would have a vertical reflection here. And I also see that our graph is getting shifted up 5. So actually all 3 of these transformations we can consider to be vertical. So our x values will stay the same, and then we multiply our y values by -2, and then we add 5. So we have -1, 0, and 1. And then here this gives us 7, 5, and +3. So let's plot those points. So we have -1, 7, 0, 5, and 1, 3. And we know that just from the general shape of our graphs that they're going to kind of make that S shape like this. And we could always plug in more points if we wanted to get a more accurate graph, but this is a pretty accurate graph. So our domain and range are always going to be all real numbers for these types of functions. And then we are done. So let's try one more together. So for this, you need to be really careful. Just remember with transformations, whenever you have a horizontal stretch, shrink, or reflection and a shift, you need to make sure you factor this number out. It can stay inside the cube root, but we need to make sure it's separate from the shift. So we're going to factor out an 8, and then it becomes x minus 2. So we can leave it like this. We can treat this as a horizontal shrink by a factor of 1 over 8, or if you notice, this is a perfect cube, and we can actually simplify this. The cube root of 8 is 2. So we could actually change this equation to say 6 times the cube root of x minus 2 minus 2. So I would recommend doing that. I think that's the easiest way to graph this problem. So we'll go from here. Again, this really only works when we have something that can be simplified within your cube root. So a perfect cube is a really nice number to see inside your radical. So let's decide what transformations we see. I see a vertical stretch by a factor of 6. We see a shift to the right 2 and then down 2. So you can see how important it is that we factor out that 8 at the beginning, or else you might look at this and say that this is going to the right 16, but again, it's only going to the right 2. So if I want to move my coordinates to the right 2, I'm going to add 2 to my x values, and then we're going to do 6y, and then, it goes down 2, so we do minus 2. So this gives us 1, 2, and 3, and then this will give us negative 8, negative 2, and 4. So let's plot our points and see what our graph looks like. So we have 1, negative 8, 2, negative 2, and 3, 4. So you can see that our graph is pretty stretched out. So when we're graphing it, we still want to try to achieve kind of that S-shaped look. So it's going to look something kind of like this. Very, very stretched out graph. But as long as you have these 3 exact coordinates and the general shape of your graph is correct, this should be good enough. So our domain and range, again, are going to be all real numbers for these types of functions. And then we are all done. So at this point, I'm going to ask you to pause the video and give this one a try. Sorry, my formatting got a little bit messed up. And when you are ready, you can hit play to check your work. All right, go ahead and check your work here. So remember, you do need to factor out the negative 3. So it becomes negative 3 times x plus 3. And then you can simplify. The square root of negative 1 is negative 1. So you can see that the double reflections actually cancel out. So you have a vertical shrink by a factor of 1/2, horizontal shrink by 1/3, and a shift left 3. So your graph ends up looking something like this. So now we're going to kind of do the opposite. We're going to look at a picture of a graph, and we're going to see if we can make the equation. So for this, I like to start by finding what I will call kind of our center point. So our center point is here, the point that was at the origin in our parent function. And our center point in this graph is 5, 3. So we can use that center point to show that our graph has been shifted to the right 5 and then up 3. So we can put those shifts into our function, but we still need to find our a value. So we have a times the cube root of x minus 5 plus 3. And here, since the a and b values are really interchangeable, you could do either. They would be different values, but you can pick either one. I will always opt to set an a value. And now we're going to substitute a point that we know, another point that we know from the graph. So let's substitute negative 3 and 2. So we get 2 equals a times the cube root of negative 3 minus 5 plus 3. So I'm going to subtract 3 from each side. And here we get the cube root of negative 8, which is negative 2. So we know that our a value is positive 1/2. which makes sense looking at our graph. We know that there's no reflection, and it does look like it has been shrunk down vertically, so that makes sense in terms of our a value. So our function will be 1/2 times the cube root of x minus 5 plus 3. All right, here's the last example for today. So please pause the video and give it a try, and when you're ready to check, you can hit play. All right, go ahead and check your work here. We can see from our center point that our graph has been shifted left 2 and down 1, so we can apply those changes for h and k, and then we can substitute the point -10.5 to help us find our a value, which is -3. So here's our final equation. All right, that is all for today's video. Thank you so much for watching.